Whenever you're ready, whenever I'm ready. Okay, thanks for your patience, and I'm happy to be here. Normally, as you can see on this slide, I did get my PhD from MIT, so it's nice to be back, even though I'm only there virtually.
What department, Daryl?
Course 2. So I was in fluid mechanics, so I knew some aero people.
I was going to say, we won't hold that against you.
Sorry?
Great.
Okay. Now, let's see. Okay, so why do you do environmental monitoring? Well, you want to make sure the air and water are of acceptable quality. You probably heard about this the past couple of days from my colleagues. You want to make sure the processing for those air and water is also working properly, and that you're providing information for feedback control. And then besides the nominal operation, there could be hazardous events that you want to detect. And then once that event happens, you want to know when is it safe to start breathing the air again. So I'll go through all of this in the next few slides. So here's a artist's conception of a lunar base, even though the sand is sort of reddish, it is a lunar base. It's the Earth there in the distance. And it's schematically got the air and water processors with actuators as needed. You want to measure the air, water, plant chambers for using food and food preparation services in case there's microbial growth. Since you're recycling, you have the hazard of the possible gradual buildup of toxic chemicals. And so the small green circles represent sensors that you want to have at least one set in each chamber of your habitat. You might have one or more that are portable devices, so the crew members can go around and find the problems if they need to. You might have a larger analytical instrument that's more capable than a simple sensor, so it's something like a gas chromatograph, mass spectrometer, or a FTIR that can detect thousands of chemicals if you need to do that sort of diagnosis. You might also have that for scientific purposes anyway. And then, as I mentioned before, you want sensors in your processing systems to make sure those are working properly. And in your airlock chamber, that rather than a chemical or microbial sensor, you might have those as well. But in the case of a lunar or Mars base, you want to make sure that you're not bringing in too much dust. And if the dust happens to be a particular chemical hazard, you want to be aware of that. And also, if in your mobile vehicles, those will likely require their own monitoring capabilities, as well as in the spacesuits themselves. And finally, all this is operating with the feedback control system. Well, by the way, interrupt with questions anytime. Wish I could see you so I could see you raise your hands, but I'm happy to take questions at any time. Okay, similarly, in a vehicle that's traveling through deep space, this is a hypothetical design for habitat that would be on a deep space mission, and similarly, you'd have your sensors in that kind of configuration. Okay, I wanted to get some pictures showing the relative size of people in their vehicles. And these are, for Apollo, these are the only ones I was able to find. So it was hard to find pictures of the Apollo capsule with people. And this is from 1950, I think. This is Miss NASA. And then here's the original Apollo astronauts. So you can tell it's, and some of you may remember, it was a pretty cramped situation. Whereas in the space station now, it's much more spacious. This is just one of the many chambers in the space station. And so let's take a look at what can happen. Well, let's say you had a leak, or maybe a fire, let out a lot of smoke. So things, the air got back pretty fast. So what the astronauts would have to do in that kind of situation, put on a breathing mask, and or go to another chamber in the space station, close off this one, and figure out how to clean up the air, figure out how that when that air is cleaned up and when you can go back in. So that's a fast time constant sort of situation. Now let's say you have a minor malfunction in your life support system. And so you get a very gradual buildup of some toxic chemical, and it may take weeks or months before it gets to be hazardous. In that case, you don't have to put on your breathing mask. You have plenty of time to diagnose and fix the problem, as long as you have the capability to diagnose and fix it. Okay, so here are some of the events compiled by my colleague Paul Mudgett from NASA Johnson Space Center that have actually occurred on the space shuttle, the Space Station Mir, and the ISS. These are as of 2006, so actually several more have happened since then. And they've happened, these are air quality issues. Here's one of my favorites. There was a metal oxide canister that's normally used to clean up the air in the spacesuit. It was accidentally regenerated when it happened to contain, this is a long story, but it contained a lot of pollutants, so they started heating it up. Normally, it would release a tiny amount of contaminants and would be cleaned up before going on the next spacewalk. In this case, it started emitting a blue smoke that smelled really bad. So that is the case when the crew members had to leave that chamber, seal themselves off, and they waited probably the better part of a day to allow the life support system to clean it up. And they didn't have a direct means of checking to make sure the air was okay, so they waited probably a lot longer than they needed to.
Daryl, quick question on these. I think this list of events is pretty interesting. Is there a classification system for ECLIS-related events, like, a Class 1 event, a Class 2 event, Class 3, and so forth, where depending on what kind of event it is, you have to take certain actions, or is it kind of more ad hoc?
Sometimes events occur that are predicted, and they have a procedure. They know what it is, and they have a procedure set in place. For example, if they have ammonia leaks, they know what that is, and they have a procedure set in place. But other things, like the event I just described, it was unexpected, and they have to figure it out as they go along.
I think, Jan, this is Charlie Kamada. I think maybe Ali's referring to the different levels of caution and warning, right, that show up on the system to alert the astronauts, possibly.
Yeah, I think that is factored into to what priority they need to take an action. I actually haven't heard that classification system apply to these events.
Okay, thank you, Daryl. Keep going.
Okay, I'll go on to the next slide. So similarly, events have occurred that affected water quality. And generally, that's although serious, it's slightly less urgent than air quality problems because basically because you die sooner from lack of air than you do from lack of water. But they're still pretty serious. Okay, so I won't go through all these, but we'll just move on here. So here's a possible architecture. If you have many modules in your space station or habitat, you wouldn't necessarily have complete monitoring capability in each module. You'd have one or two highly capable analytical instruments, and then a simpler but more robust sensors in each of the modules. So you have a certain amount of redundancy because you have many modules. But that's something for when the people in this workshop who are trying to design your mission. This is the kind of consideration to take into account. Do you want to have? Is it worth having an analytical instrument in each module for whatever reason? Or maybe you know of some technology that you think will be ready by the time your mission flies. And I'll get into that kind of issue later. Okay, so this is what we currently have done. We take, in order to measure the contents that are in the air, we take a grab sample. It's an evacuated stainless steel canister. It's, you open it up. The crew member manually opens it up. It sucks in a sample. Then they close the valve and they store up several of these per month, and they send them down. They had been sending them down on the space shuttle, and they get analyzed by a large, ground-based chem lab. They have had some in-flight capability. One example is formaldehyde badges, and so those actually did detect an increase in formaldehyde that was a problem. Here are some of the air monitors that are so-called operational, meaning they're approved for making flight decisions. There was the volatile organic analyzer that measures trace organic chemicals. There's the separate that works by ion mobility. That's no longer in use, but it was used for a few years. A major constituent analyzer, which is a magnetic sector mass spectrometer, is still being used. It measures the major constituents of the air, which are nitrogen, oxygen, carbon dioxide, water vapor, some degree of detecting methane as well. And then there also have been some experimental devices tested on the station, and I think all of them worked reasonably well. The European Space Agency tried out a Fourier transfer infrared spectrometer. There was an experimental device to measure gram-negative bacteria from various surfaces. This device is still up there, but it's just recently turned off after being in use for about 2 years. That's the VCAM, Vehicle Cabin Air Monitor, which is a GCMS. I'll say a little bit more about that later. The CSPE, colorimetric solid phase extraction, that is in use as well. You take water samples and you make sure that the biocide, which was used to treat the water to remove bacteria, has been removed to a safe enough level so the crew members can drink it. That would be silver on the Russian side and iodine on the American side. And then there's the electronic nose, which detects a wide number of chemicals, has a fairly robust, simple architecture. Okay, and here's a few more that I didn't manage to get pictures of. Okay, now I wanted to get into a case study, and I was hoping to get audience participation, and since I can't see you, this could be a little tricky, so I guess we'll see how it goes. But this is going to be nanotechnology, has some legacy of terrestrial usage. It's self-repairing. Anyone want to shout out a guess about what this might be? Use your imagination.
Do you want to press?
Carbon nanotubes.
Okay.
Yeah.
That's a possibility. Any other guesses?
Your nose.
Sorry, I didn't get that one.
Your nose.
Your nose. Oh, that's a good guess. Any others? Okay, well, I think the nose was the closest. Oh, by the way, here's one last clue. This approach does have local intelligence, memory and data processing. I guess all this would apply to a nose. And in fact, it's canary, which has a nose. Okay, everybody has heard of the canary in the coal mine, and that really can work. So here's where we can have some more audience participation. So why would a canary be good for monitoring chemicals in space? What would be good about a canary?
The canary would die before the astronaut would.
That's good, yes.
It doesn't compete too much for the food supply.
Oh, very good. Okay, so we have the canary being smaller, probably is more sensitive to trace gases in the crew, and also because it's small, it doesn't consume very much food or water or air.
And
Anything else?
it could also be used as food.
Well, very good. Yes, if you're really in a pinch, you could probably eat it.
And they're quite cheap, and that wasn't meant to be.
Oh, I didn't quite hear that one.
They're cheap. Don't cost very much.
Oh, they're cheap. Yes, yes. Okay. This is all very good. So they're not expensive. So in fact, maybe you can have more than one. Okay. So here's what I have listed, and you've caught several of them so far. So it works. I wrote that it works continuously. Right. It doesn't just work like once a day or once a week, but it's on all the time. It has ground-based heritage, so people have a history of its pluses and minuses. Doesn't require a skilled operator, unlike a gas chromatograph mass spectrometer usually on the ground, or an FTIR usually requires a skilled operator. As someone noted, low mass and low power, so they don't demand much and they're cheap, and so you can consider placing them in different modules. As someone else mentioned, they're more sensitive than the crew, so that's good. Multifunctional, so they detect components in air and water, and they can provide some entertainment. Probably works in microgravity. I haven't heard of anybody flying canaries, but they have flown other kinds of birds, so they survive.
Could be messy, though.
Could be messy. Oh, we'll get to the disadvantages on the next slide. Okay, built-in signal processing with its bird brain, and as someone else mentioned, it's probably edible. Okay, so what are the negatives? So one person said it would be messy. You have to deal with cleaning up.
You'll have a limited supply of them. I mean, eventually, if you have too many mistakes, then you run out of canaries. What do you have? What do you have then?
Okay, that's good. So yeah, if you could run out of canaries, and well, I suppose if you kept a family of them, maybe they'd reproduce and you'd grow a new one.
They make
But that is a thought.
viruses, bacteria, feces.
Yep. So that's a good thought. They could carry bacteria. They could bring some illness to the crew, like bird flu.
They'll start chewing on your electric cables and pecking against the thin walls and making holes in your hull potentially.
Oh, if you let them fly around, they might misbehave. Okay. Let's hear one more.
One more.
I might get to care about the canary, and if it dies, I'll be sad.
Oh, that's a nice one. So yes, so it's the relationship with the crew. I mean, it has its pluses and minuses. It may make the crew happy while it's alive, but then they'll be sad if it dies. Okay, so here's what I listed, and we've gone through this one before. It does require some food, water, and maintenance, including cleaning up the messiness, which is generation of waste products. Okay, if it dies, you need a complete system replacement, meaning the whole new canary. Not sure if it's how quantitative you can make it. Limited life. Okay, it's probably hard to interface to your computer network if you want to do that. A low precision display. That could be hard to read in microgravity. So normally, if it is used in the coal mine, then it passes out and falls to the bottom of the cage. But in microgravity, it might look like this, and you wouldn't necessarily know right away that you had a problem. Okay, so that's our case study. So what's our situation now? Well, with the space station, we have had the shuttle flying, and we would bring supplies up and bring the grab sample containers down for analysis in a chem lab. And let's see, I guess you guys are working on a trip to Mars. But if you're going to Mars, then you don't have any capability of sending things up and down every month or two like we have been doing with the space station. And of course, we don't have the space shuttle anymore, so our capability to bring things up and down is now quite a bit more limited. So we really need that in-flight capability of monitoring much more than we have in the past. Okay, now a little bit more detail about a couple of the instruments. So this is the VCAM, Vehicle Cabin Atmosphere Monitor. It's a gas chromatograph mass spectrometer. For those of you who are into chemistry, you probably know what that is. That's what it looks like on the space station. It's probably a little smaller than the ones you buy for your chemistry lab. Like most GCMSs, it's capable of detecting really thousands of components. It's actually calibrated for well, I'm getting ahead of myself, for a finite list. And it measures not only trace gases, but also the major constituents. And so that's some pictures of what some of the insides look like. You could also take some of these disposable bags, and if you want to make a measurement in a different module, you inflate the bag, bring it over to the UCMS, and you can get it analyzed. Okay, so this is the list of target gases that it was calibrated for. But like any GCMS, it's actually capable of detecting quite a few more. And it's only a matter of how many do you want to calibrate it for. So it's quite a versatile instrument. And again, for those of you who are chemists, you might want to see the ion chromatograph. The gas peaks come out with time like any other GC, and then each individual peak has its own mass spectra. And we show one here. The first one was for fluoropropane, and then each successive peak also has its own mass spectra that's run by a library from the National Institute of Standards, and you can figure out what you have and how much there is based on the area under the peak. Okay, a different approach is the electronic nose. It's quite a bit smaller. Actually, the device itself is in this section over here, and the big white box, which is relatively big, is the space station interface. The space station program was actually pretty happy that it was this size. Personally, I wanted it to be a lot smaller, but because they have so much room on the station, there was no problem with the box this size. And so, theory of how it works in the lower right, you basically have an array of polymers that are semi-selective, and so each of them changes in resistance in response to what's in the environment. So on the blue peaks, we have those 16 sensors, and the blue peaks are the response change in resistance to toluene, which is chemically pretty similar, except for the methyl group, to benzene, which is the sort of pinkish peaks. And so you can see the pattern that's of the sensors is similar for toluene and benzenes, but it's also a little bit different. Number 1, 13 are very different. Number 2 and number 8 are pretty similar. So if you program this ahead of time, you can actually figure out what gases you're detecting. You can look for a particular set of gases. So for that matter, with sufficient theory behind it, you can sometimes back calculate, given a particular pattern, what caused that pattern.
Hey, Dr.
So
Young.
the nice thing is,
Dr. Young,
yes, the question?
Yeah, this is Charlie Camarda. The reason why I said nose was because I thought I heard that the crew can detect an ammonia spill earlier than maybe the instrument. Is that true? And the follow-up question is, a lot of these ideas may be biologically inspired design, the sensors in biological organisms, for instance, and with nanotechnology, are people looking at developing sensors using nanotechnology to maybe mimic some of the biological systems?
Okay, so two good questions. So certainly some crew can detect ammonia at a pretty high sensitivity. If you look at the documentation of odor thresholds, certainly some people are pretty sensitive, but there's also quite a orders of magnitude variation from person to person, or from a given person. Depends on what your health is. Maybe you have some congestion, or maybe you're asleep, and then your capability is quite diminished. So it's quite variable, and you really don't want to be in a position to have the crew nose be your only detector. Regarding biologically inspired, certainly this architecture is biologically inspired. The original concept was St. Louis at Caltech, and refined into quantitative form by Dr. Amy Ryan at JPL. And so, and in fact, I mentioned there are many different polymers comprising the set of array of sensors. And in fact, of the one we flew, one of them did use carbon nanotubes as its conductive dopant, and the other ones that didn't use carbon nanotubes, they did use not nanotubes, but they were nanoscopic particles of carbon. So some of that nanotechnology research has gone into this kind of device. It is continuing, although there are budget constraints.
Thank you.
But as far as the general thought of leveraging biotechnology and bio-inspired design, that's actually, I want to say more about that in a few slides later. But any more questions right now?
That's great. Thank you.
Let's see, that's just a picture of the electronic nose mounted in the space station. It detected some events, none of which were hazardous. The most amusing one was right around the Christmas and New Year's time frame. We noticed a surge in the appearance of ethanol vapor. So we thought perhaps the crew members were celebrating. Okay, so here's some thoughts to consider for when you're doing your own design. Oh, we're running late. Let's see. I would think about 10 or 15 minutes. Thanks. Okay, so there's a trade-off to make. You'd like to be able to, certainly the toxicologist would like you to be able to analyze for nearly anything. But on the other hand, that's more expensive, and the instrument is more complex and maybe harder to maintain. So do you want to go for a simpler architecture like the electronic nose, for example, or even maybe even something simpler than that? If you feel confident that you can get by with only measuring a few things, maybe you'd want to do that. And then the second bullet is I put that because I often get approached by people who said, "Here's my technology. It's really great. Solve all your problems." And it turns out it's a nice technology. It'll solve a part of the problem, but you really have to have the whole solution. For example, at one point I was told, nanotubes are great, but they didn't tell me what do I use it for. So we had to have the solution for the rest of the problem. And there's more than one way to use them, as I'm sure you're probably aware. One of the ways we use them was in the electronic nose polymer, but there are other ways to functionalize the nanotubes and make a different kind of sensor out of it. Okay, so we've talked about leveraging what's going on in bio-inspired biotechnology, and I wanted to talk about technology progress in general. So let's think of this curve as technology progressing with time. So microelectronics get smaller and faster, computers get smaller and faster and cheaper, progressing with Moore's law, so not at a precise rate, but it gradually goes up. And let's say you have your set of space missions. Maybe your mission to Mars is here. Maybe you have a robotic mission here. Maybe you have a mission to one of the lunar Lagrange points here. So you have those scheduled into your time frame. And if you want to fly a given technology on those missions, you have to give yourself time to make that technology flight ready, so that it has to survive the intense vibrations of launch, has to survive the space radiation environment, and it has to be you have to make sure it doesn't outgas into the crew environment, and it has to work in microgravity. A lot of things like that. So that usually takes some time. Could be 1 or 2 years. And so what you do is you freeze the technology and give yourself time to adapt to flight. So that's a necessary thing. It does mean that when you're flying your mission, you're actually not able to carry the latest technology, which is going to be up here, for example, for mission number 1. Okay, similarly, let's say you pick a technology, and maybe you picked you had good success with a solar cell that worked really well here, and you want to use it for your next mission. And so you're hoping to use it for mission 2 and mission 3. But by the time you get to mission 3, a newer technology is available. It's so much better that in the commercial world, technology A went out of business, and you can't get those anymore. Even though you like them and they work well, they were very reliable. So you have to adapt to technology B, and hopefully its ground requirements and its flight requirements are going to meet your needs. And this kind of thing happens a lot. Okay, size matters. So this is the concept of a lunar lander, which was developed during the Constellation program. So this is a more capable lunar lander than we had for Apollo. You can see it's quite a bit larger than the Apollo lander. And then I want to put it into scale with the space station. So that's roughly the scale. So you can see the even compared to the larger size Altair lander, the space station is still looking pretty big. By more than an order of magnitude. And so remember the size of the instruments that were on the space station. So this is in a rack. These are about, sorry, I don't know the metric, but I think it's about 19 inches wide, like a typical rack. Same with this guy. And those are their sizes. And so, the Altair lander also had to monitor air, but because the volume of the spacecraft itself is so much smaller, the mass allocation for air monitoring was about 10 to 30 times smaller than we had for ISS. So they needed much smaller technologies for doing the same function. And that's whatever vehicle we choose, it's probably not going to be, you probably won't be able to afford a space station-sized vehicle going to Mars. It'll probably be closer to this Altair-sized vehicle. And so you're going to have to do some pretty serious miniaturization compared to what we had on the space station. Okay, so that's a summary and conclusion. If you have more frequent missions, which we sometimes have thought about doing, you'll have to make more frequent technology decisions. You have to choose your point. When do I freeze it? When do I develop it for flight? And biotechnology and the microelectronics industry are progressing rapidly. You want to make sure you keep abreast of those things so you can take advantage of what you can. Any questions?
Darrell, I have one of the things you mentioned early on, which I think is very important, is the need for integrated health monitoring, especially for a mission to Mars, where you are going to be highly autonomous as opposed to missions we've done in the past, and also the need to be highly reliable. Does the rest of the agency concur and agree and putting a high enough level of effort into that research?
So yes, you do need a high degree of reliability, and that's recognized. I think that should have been in the TA06 document, which some of you have heard about. So that's the Office of the Chief Technologist of NASA. That's their technology roadmap. They point out that reliability of the life support system is a very high priority. There is some disagreement about how to achieve that high reliability. Some people say that if it's reliable enough, then you don't have to monitor. You just have such high reliability that nothing will go wrong. And that's a laudable goal. A lot of people will say, well, that's what you want to try to achieve, but you're never going to get there in practice. And so you have to have some monitoring to make sure you're checking for things that might go wrong. It's sort of like the philosophy of you want to design it so you're sure you're not going to have a fire, but you still might have a fire, so you better have a fire extinguisher just in case.
It looks like compartmentalization in a spacecraft is a big advantage. In other words, if the more compartments you have, the more opportunity you have, if there is a problem, that you can shut off one of the compartments.
That is true. On the other hand, it probably costs you some money to compartmentalize. So there's probably an optimal point. Every time you compartmentalize, you'll have to have doors and feed-throughs and all that.
A question, how do you deal with redundancy in terms of reliability? And do you do fault tree analysis to figure these things out?
Oh, yes, certainly. So you do a trade study, and you look at, if I put my money into, is it better to put my money into making a single device more reliable, or should I have two of them or three of them? So you have to do those studies. It could be a fault tree or a number of other approaches, like you suggest. Some probabilistic failure analysis could be relevant. If you could do some ground testing for getting a better handle on the quantitative nature of your reliability, that's helpful for making a decision. On the other hand, ground testing does cost money, so there are all these trade-offs to make.
Well, do you do test-to-failure experiments with the equipment you buy? Do you know what I mean?
Well, in the broad sense, yes and no. So, there's a whole range of things that are purchased, and if I'd say the more critical they are, then the more testing you do.
Well, by that I mean, for instance,
also, go ahead.
If you have an instrument for an extreme environment, do you put it in there and see under what conditions it fails? You do much testing like that?
So I don't think we necessarily test everything to failure. Let's see, in the context we're talking about now, in the crew habitat environment, everything has to survive. Normally you don't get exposed to vacuum when you're in the crew habitat, but in case of emergency, it could happen. So everything that goes into for example, into the crew habitat has to be able to survive exposure to vacuum. So it doesn't have to necessarily function while it's in vacuum, but once the atmosphere is restored, it has to regain its capability.
All right, Dr. Yan, I want to...
There's requirements for temperature extremes and electromagnetic interference and things like that.
Dr. Jan, I want to thank you for getting up so early at JPL and giving us this excellent lecture. If you could send us your slides and any other useful references, we will post them. And hopefully you can entertain some questions, maybe virtually, from some of the teachers here as we create some curriculum for the students.
I'll be happy to do that, and it was a pleasure.
Thank you so much.